Okay, just look at this setup here, guys, to make sure you've got this. Okay, essentially what we're dealing with is again, an inclined plane here that the rock would be at the top of, right? So we're dropping it. Okay, it's starting from rest, and we need to figure out how high it's dropped from in order to achieve a speed of 4.5 meters per second here at the bottom. Okay, so at the end of the tunnel. Remembering that we do work against the force of friction, which is considerable, 800 newtons, okay, over a distance of 30 meters. That means we're losing energy between the top of the ramp here and the bottom of the ramp to friction. So it has less mechanical energy at the bottom of the ramp than it had at the top. Okay, so we need to figure out that initial height. Okay, that's what we're looking for there. Remembering that work is a change in mechanical energy. All right, so that's going to mean force times distance equals EP final plus EK final minus EP initial plus EK initial. Right, that's what we're starting with, and we're trying to find the initial height that the rock was dropped from. I'll give you a couple more minutes and then I'll walk through the solution. All right, so we know that we're losing energy between the top of the ramp and the bottom of the ramp because we're losing it because of the work done against the force of friction. Okay, so what we're going to have to find is HI, okay, because that's what the question wants us to look for. So if we expand out that formula some more, force times distance, the force of friction that is, times distance, is going to equal m times g times h final plus 1/2 mv final squared, okay, minus m times g times h initial plus 1/2 mv initial squared. All right, so the first thing I want to do is know that I'm solving for HI here. So I'm going to move the MGHF, the whole final energy, over to this side by subtracting it. Okay, I'm going to subtract it over to this side because right now it's positive. Okay, so I'm going to bring it over to this side here, and I'm going to have that the work done, okay, minus the final energy should give me the initial. And in this case, okay, that'll work. So minus mghf plus 1/2 mvf squared equals, okay, our negative mghi, okay, plus 1/2 mvi squared. Now, I'm going to start eliminating some things because I moved a bunch of stuff that I don't actually need. How much kinetic energy is there initially? 0. All right, so there's one less thing to worry about. Okay, and how much potential is there at the end? 0. All right, so if I take the work and I subtract the final energy, okay, that should give me the initial energy. Everybody all right with that? Yeah? Okay, so now I'm looking for HI, so I'm going to divide both sides by m times g. Okay, that'll get rid of that. Okay, and then I should be able to find, okay, what I'm looking for. Now, I got to remember here that my work is positive or negative in this case? Negative, because it's the force of friction, it's losing this energy. Okay, so when we're plugging in our numbers here, that's going to be 800 newtons times 30 meters minus 1/2 times 400 kilograms, the mass of the rock, times 4.5 squared divided by 400 times 9.81. And that'll give me HI. Okay, so 800 times, actually negative 800, sorry. Negative 800 times 30. Okay, minus 0.5 times 400 times 4.5 squared. Okay, and then we're going to divide that by 400 times 9.81. Whoop, and I got to put that in brackets. All right, so I shouldn't have got a negative there, but I did. Okay, 7.14 meters. Okay, actually meters, okay, is the height I need to drop it from. Okay. The reason that shouldn't have come out, what did I mess up? I messed up something somewhere. Yeah, but I don't ever make G negative when I do these. So. Oh yeah, I forgot to bring, yeah, that's what it was. Yeah, I should have brought the negative over. I didn't bring the, yeah, you're right. I didn't bring the negative over. I crossed it off here and didn't bring it over. So the reason I got a negative answer, guys, is I forgot to bring this negative that I crossed off over. This whole bottom thing I should have made negative because it was effectively 0 minus that. So that's why it came out negative and shouldn't have. I just neglected to bring a sign over that I shouldn't have. Okay, so 7.1 meters is the height that it should have dropped from. And that should be fairly realistic because as we saw in that clip on Friday, he looked up quite a ways to see that rock when it first started moving. Okay, it was definitely quite a bit higher than he was. All right, so are we getting this whole work is a change in energy thing? Okay, I mean, this is kind of the final step. This is as hard as they would get as the types that we did on Friday and this one. Okay, but there's obviously some easier ones like you would have done in Science 10, just force times distance kind of thing. So I want to spend a little bit of time working on those before I review energy in depth. Okay, because probably tomorrow, Wednesday-ish, we'll be working on conservation of energy. Okay, we'll have a lab on conservation of energy sometime coming up here as well. Okay, so we'll be definitely finished this unit Tuesday. Okay, possibly before that, but definitely we'll have all the material Tuesday. So I will do a unit exam review this Friday. Okay, and I will put the unit exam review package on Google Classroom today or tomorrow. Right, so that's what's coming up for you guys. Okay, so the ones entitled work here, they're on page 5 of the Dynamics workbook, okay, near the bottom. Okay, there's only 8 of them. They start out really easy. Okay, it's just like force times distance kind of stuff, but they'll get more complex as you go down. Okay, towards numbers like 6, 7, and 8. Those will be more like what we just did, right? So that you get a taste for all of them. Okay, guys, let's talk about the first few here because they're obviously fairly straightforward. Okay, in question number 1, we have a 20 Newton object lifted, and the key words here are at a constant velocity. Okay, 1.5 meters. How much work is done on the object? On Friday, we talked about how you don't have to accelerate something in order to change its potential energy, right? As long as I lift it at a constant velocity, okay, I'm exerting the same amount of force upwards as gravity is pulling down with, just like the barbell, right? The 710 Newton barbell we talked about. I only have to exert 710 Newtons worth of force to move it upwards at a constant velocity. If I exert more force than that, then I will also change its kinetic energy. Okay, so in this case, we calculate the work done by taking the 20 Newtons of gravity and multiplying it by the height. Okay, force times distance, or m times g times h. It's just that 20 Newtons is m times g. They already did that for us. Right, in number 2, okay, we have a 15 Newton object moved horizontally 3 meters across a level floor. As soon as they say it's level and horizontal and all that, the weight of the object becomes irrelevant. I'm not changing its potential energy if I'm dragging it horizontally. So the only force I need is this horizontal force here, 6 Newtons. That's why the answer is 18, 6 times 3. Okay, force times distance. I didn't change the potential energy, so I don't need to know anything about the vertical forces in that question. Now, number 3 is both a work energy theorem question as well as kind of a Newton's first law question. Okay, how much net force is required to keep something moving at a constant velocity? 0. Well, that's what's going on here. Okay, a 2.2 Newton object is held 2 meters or 2.2 meters above the floor for 10 seconds. So does it take any work to hold it there? No, it doesn't. Okay, I'm not changing the calculator's energy at all. I'm not making it go faster. I'm not making it go higher. So I'm not doing any work on it. Okay, that's why the answer comes out to 0 joules. You're not changing either form of energy at all in this question. Okay. And then for number 4, okay, that one there is one of those net force is what changes the kinetic energy of an object questions. Okay, and we talked about that on Thursday. Okay, we have a 10 kilogram object. We can accelerate it from rest to 11 in 5 seconds, so we can calculate its acceleration. Okay, and the net force would be mass times acceleration times distance. That would give us our work done in that one. Okay, are these sort of making sense? Right, so they're the same things we talked about on Thursday and Friday. Okay, just different applications of it. All right, keep going there, guys. Let's finish those up and then we'll talk about them. Okay, so on question number 9, we've got this box sitting on a level surface. Okay, so it says a level floor. We're going to move it 6 meters. We're going to do that in 4 seconds. And we're going to start from rest. Okay, so what can I find right off with those 3 things? I have VI, I have D, and I have T. Okay, I could find that, but I don't want it. I can find acceleration, right? Remember, I'm changing the kinetic energy of this object. I'm accelerating it. If I'm going to find the work done or the change in kinetic energy, I need to know what the net force is, right? So my first job here is to find acceleration so that I can find what F net is. It's m times a, right? When I find the change in kinetic energy, that's work. That'll be F net times the distance, right? So first I'm going to find acceleration. Acceleration will be d over half of t squared. Okay, that's because that's d equals vi times t plus 1/2 at squared. So that's just manipulated for a. So we'll have 6 meters over 1/2 times 4 squared. And what does that come out to? So 6 divided by 8, that's 3/4. Okay, it's 0.75. Okay, 0.75 meters per second squared. All right, so now I'm going to calculate my net force, 0.75 meters per second squared times 25, which should be 18.75? Yeah, 18.75 newtons. That's my net force. All right, so I can calculate the work done in changing the kinetic energy by just going F net times D. Okay, that'll give me the change in kinetic energy. So that'll be so 18.75 times 6. So what, 100 and some 130? No, it's not 135. It's 18.75 times 6, 112 or something like that. Yeah, 112.5. Okay, so we got 112.5 joules worth of work being done just to accelerate the object. That's not counting, however, the amount of work we have to do to also overcome friction. Okay, friction is present. It's an additional force that we are working against that will require additional work. Everybody follow me there? Okay, so what I have to do then is also calculate the work done against the force of friction while this thing is being accelerated. Okay, so that's 3.8 newtons times 6 meters. Right, which is another 22.8 newtons, or sorry, 22.8 joules. If I add those together, now I get 100, well, it should actually be 136, okay, joules worth of work for the entire thing. Okay, everybody follow me? We can't forget that we also had to overcome friction and then accelerate the object. Okay. All right. Any other ones on there that were giving us trouble? Okay, then let's quickly review the types of energy here. Okay, so hopefully this will seem familiar to everybody. Okay, so potential energy is, well, there's different kinds. Okay, gravitational potential energy is based on 3 things. The mass of the object. Okay, I mean, think about it. Which would you rather have to stand under? Okay, if it was falling off a building, a tennis ball or a grand piano? Okay, I picked the tennis ball, right? I mean, it'll hurt a little, but it won't kill me. Okay, I'd much rather stand under something less massive because something less massive has less ability to do work. Okay, the second thing that can affect gravitational potential energy is gravity. Okay, in a place where gravity is stronger, being the same height off the ground means that it would have more energy. Okay, now on Earth we don't worry about that too much because we consider every point on Earth to have the same gravitational acceleration. That's not true, okay, but we simplify it to be that way. Okay, and then the third thing is the height. 2 tennis balls are being dropped from a building. I'd rather stand under the one that was only dropped 1 floor than 20. Okay, it'll be moving a lot less fast when it hits me. Okay, so yeah. Okay, those are the 3 things that can affect gravitational potential energy. There's different kinds of potential energy. Okay, there's the elastic kind that we'll talk about in Unit 4. Okay, but for right now, we're just going to concentrate on gravitational potential energy. Now, we talked about this relationship here the other day. Changing the potential energy of an object requires work. Work is force times distance, and the force we work against is gravity, and a vertical distance is a height. Okay, so this is why force times distance is equal to, okay, the same formula as the potential energy formula. When I do work against the force of gravity, that's what I'm changing. Okay, everybody okay with that? Okay, so in this example here, fairly straightforward when you've done one like this in Science 10. Okay, if the passengers and the car have a mass of 500 kilograms, okay, we're trying to calculate their change in gravitational potential energy if they're lifted 48 meters. Well, that's going to be 500 times 9.81 times the change in height, 48.0 meters. Okay, essentially we're saying this, m times g times h final minus m times g times h initial. But in reality, I'm multiplying both of them by m times g, so I could just say m times g times the change in height and get the same thing. Okay, so we'll have our number here, 500 times 9.81 times 48 meters. All right, they got a lot of potential energy, but it's a lot of mass too. Everybody's okay with that? That's not something hard. Okay. All right, so on this one here, okay, we're talking about the importance of a reference point. Sometimes when they give you heights, they refer to the ground, and other times they are, I lifted it from this point, which was above the ground, to this point that was above the ground. What's my change in potential energy? Well, the change in potential energy is only from where you started to where you finish, not all the way from the ground. You didn't lift it to the table first. Okay, so we have to understand that we always have to read a question in order to get where the question is starting from. We don't always assume it's from ground level, okay, unless we're told so. Okay. So what's the gravitational potential energy of the car, which has a mass of 0.0250 relative to the floor? So now they're saying, okay, so when it's on top of that thing, all the way to the floor, what's its potential energy? They told you, here's the reference point. The reference point is ground zero. Okay, and then for part B, it says calculate the change in gravitational potential energy of the car when it arrives at the bottom of the hill. So now our reference point is no longer the ground, it's the table. Right, so it's important to know, okay, when we read a question where we're going, because you can do all the work right, but have the wrong number in there and then get the question wrong. All right, I want you guys to try question 1 here first, okay, about the Piledriver. Okay, a Piledriver is not the wrestling move, which oddly enough quite honestly mimics what a Piledriver really does. Okay, a Piledriver takes a large mass and takes it up to a high height with a crane essentially, and then drops it onto a piling and pounds it into the ground. Okay, hence Piledriver. Right, when they were redoing the bridge down here on 549, okay, that down at the bottom of the hill down there, okay, that you could hear in the summertime, you could hear them using a Piledriver. Okay, anywhere in town you could hear the clanging of that Piledriver hitting those metal pilings into the ground. Okay, so that's what this question is about. Okay, we're taking a 550 kilogram Piledriver, 12.5 meters above the ground, and it's going to hit a pile that is 2.30 meters above the ground. Is it falling all the way to the ground? It's not. Okay, that's kind of the key part to that question. All right, so it says relative to ground level, what's the gravitational potential energy of the Piledriver at its highest point, at its lowest point, and what's the change when it is lifted from the top of the pile to its highest point? Okay, so give me a minute here, quickly calculate those. All right, so this one's not too terrible difficult. Okay, The big thing here is it says relative to ground level. Okay, all the numbers we're given, okay, are relative to the ground, so we can just use those. So we'll have m times g times h for the first one. So that'll be 550 kilograms times 9.81 times 12.5 meters. All right, so it's got 67,443.75. Joules of energy at its highest point. Okay, at its lowest point, same numbers except the height changes. So 550 times 9.81 times now 2.30 meters. All right, so we got 12,409.65 joules worth of energy when it's on top of the piling. And then how much, what's the change in gravitational potential energy? Well, we just subtract those two numbers. So 67,443.75 minus. All right, so we're looking at a change of 55,000 joules roughly. I think we have three significant figures there, so 5.50 times 10 to the 4 joules. Okay, questions on that one? Okay, not too tough. All right, number 2 is also not very mathematically difficult, okay, but is going to require you to read the question a little bit more carefully, okay, in order to get it right, and then try number 3 after that. So with this one here, the roller coaster begins its journey 5.25 meters above the ground. Okay. Then at the end, it says, how far from the top of the hill, or how far is the top of the hill above the ground? Well, if I look at this number only, this number is only from, so if here's ground level, this number here only includes from the start of the train to the top of the hill, and I'm wanting the whole thing. So I've got to find out how much energy the train has here as well and add it on to this number in order to calculate the final height. Okay, it has to be measured from ground level. This change in energy is only from here to there, okay, and would only give me the height above the starting point, not the starting point, not above the ground. Right? So I would first have to calculate how much energy it has when it's 5.25 meters above the ground. So what we got here, 875 times 9.81 times 5.25. Okay, that'll be okay. So there's the energy. Sorry, it's supposed to be 875, not 570. 875 times 9.81 times 5.25. All right, so there's the initial energy. Then I'm going to add on to that the change in energy that they gave me, which is 42,000. Oh. All right, so there's the total change in energy from the ground. Okay, now I can take that and divide by m times g. So that'll be 875 times 9.81, and that will give me the height above ground level, okay, which is 54 meters. Okay, 54.2 meters. Okay, how many people have done number 3? Okay, keep going on number 3. It sounds harder than it is. There's really only 2 mathematical steps to it.